Today, we want to continue looking at the interval of convergence for a power series. We know that we can use the ratio test to find the interval of convergence for a power series, but we want to be able to determine the interval of convergence without doing the ratio test, because it's a lot of writing. We have to cancel some stuff out, and anytime we start doing algebra, we start introducing the possibility of making mistakes. We want to be able to determine the result. So another way to think of it is we want to be able to determine the results of the ratio test just by looking at the power series. So let's continue to talk about our strategy. Our strategy is going to be look at the coefficients in the power series and identify any factorial factors, any exponential factors, and any polynomial factors, and know what those factors are going to do to the interval of convergence. At the bottom end of the things, we have polynomial factors which just affect the endpoints. This makes sense because we're going to be running the power series through a ratio test, not like by writing everything down in our mind. And the ratio test is blind to polynomial factors. The ratio test, when it sees polynomial factors, that limit is always 1. The limit as n goes to infinity of an plus 1 over an, when an is a polynomial or a rational function or a radical function, that limit is always going to be 1, which in the ratio test tells us nothing. The exponential factors are going to tell us about a finite radius of convergence. We're basing our analysis on geometric series, and so our basic interval of convergence is the interval from -1 to 1. That is the interval centered at 0 with a radius of 1. So exponential factors could affect the size of the finite radius of convergence. The other possibility is that the radius of convergence is 0, that is the power series only converges at its center, or the radius of convergence is infinite, which means the power series converges for all real numbers. For this to happen, we need to have factorial factors. And we haven't looked at those examples, so that's where I want to pick up today. I want to look at a power series with a factorial factor, and we're going to see how factorials behave when they go through the ratio test. So let's consider the series n goes from 0 to infinity of x to the n over n factorial. So that'll be 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. We're trying to build an intuition for what's going on. When we see the x to the n, that means we're going to be centered at 0, and we always start with a base radius of 1, because that's if this n factorial wasn't there, then this is a geometric series with a common ratio of x, and we know a geometric series converges when the common ratio is less than or is strictly less than 1. But then we look at the coefficient. The Cn has a factorial in it. And factorials mean we might have a 0 or an infinite radius of convergence. So let's run this through the ratio test to see what happens. That is, let's do the thing that we're trying to avoid so we can see how to avoid the thing. So we're going to do a ratio test, which means we'll take the limit at the limit as n goes to infinity of the absolute value of an plus 1. So x to the n plus 1 over n plus 1 factorial over an x to the n over n factorial. So I'm going to separate like with like. I've got my coefficients. So I've got an n plus 1 factorial and in the denominator, and an n factorial in the denominator of the denominator. So I'm going to have an n factorial over an n plus 1 factorial. The other like with like is an n x to the n plus 1 and an x to the n. That's where we're going to have some simplifying stuff. And now we just want to simplify things. X to the n plus 1 over x to the n. This is like x to the 10th over x to the 9th. That leaves an x to the first. Or an x to the 100th over x to the 99, which leaves an x to the first. In either case, when we simplify x to the n plus 1 over x to the n, there's no more n involved. So this can be pulled out of our limit. So the other thing we need to simplify is n factorial over n plus 1 factorial. The way that factorials work, we can always simplify, start writing out the bigger factorial until we get to the smaller factorial. The smaller factorial is always a factor of the bigger factorial, because the top will be 54321 and the bottom will be 654321. So the n plus 1 factorial has n factorial as a factor. So the smaller factorial is a factor of the larger factorial. So our strategy for simplifying factorials is to write the bigger factorial until we get to the smaller factorial. So I write this one out as n plus 1 times n factorial. And since the smaller factorial is a factor of the larger factorial, that's why the n factorial cancels out. So we'll have the absolute value of x from the x to the n plus 1 over x to the n. And I take that out of the limit because it no longer involves n. And then the stuff that does involve n is just 1 over n plus 1. Since the n's are all positive, I can drop the absolute values. But now we can see that the limit from the ratio test is equal to 0 regardless of the value of x. And 0 is always less than 1. So the limit from the ratio test is always less than 1. So the power series always converges. So the limit from the ratio test is equal to 0. So the thinking is the limit from the ratio test is 0 for any value of x. And 0 is less than 1, because that's the comparison that we want to make in the ratio test. Therefore, the power series converges for all values of x. That means the interval of convergence is all real numbers, and the radius of convergence is infinite. This is a result that we got from running the ratio test, but we want to be able to see the result of the ratio test just by looking at the power series. We're trying to do enough ratio tests so that we don't have to do the ratio test anymore. This is the point of being in a math class. You want to learn math well enough so that you don't have to do the math anymore. And part of being knowledgeable about math is knowing when you don't have to. It's about building an intuition. Because we don't come programmed with an intuition about how numbers work, especially when things are very large. Any questions? So going back to when we first looked at this power series, we'd see the x to the n. We know that x to the n puts our center at 0, and our default radius is 1. Any exponential factors will tell us to increase or decrease the radius of convergence. But then we see this factorial factor, n factorial in the denominator, and no factorial kind of in the numerator to cancel it out. So that tells us that we're going to get an infinite radius of convergence, because that n factorial in the denominator. The thinking is that n factorial in the denominator is going to make the limit from the ratio test equal to 0 for all values of x. Note that even if we plug in a 100 billion for x, there's when n is a million, we have a million factors of 100 billion. But in the denominator, we have n factors of numbers that are going to be, we're going to have to go n larger than x. I got those backwards. When x is a million, that won't matter. When n gets past a million, we have the same number of factors, but where the number of the factors in the numerator are all copies of a million, down in the bottom we've got 100 billion copies of, or 100 billion factors starting off at 100 billion. I should use smaller numbers so I don't confuse myself. In the numerator, I'll have like 10 copies of 2, but in the denominator, I'll have 10 factors. Most of them are bigger than 2, because the numerator would be 10 2s. The denominator will be 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. So most of the factors in the denominator are going to be bigger than that of the numerator. I could have deployed that sentence a little bit better. So we're still thinking factorial defeats polynomial, defeats exponential, which defeats polynomial. The goal is just to learn to read the factors in the coefficient. So for example, let's suppose that we have a series as n goes from 0 to infinity of n to the 5th times 3 to the n times x plus 2 to the n over n factorial. So there are things that we notice. First, we notice that the center is at 2. Or sorry, -2. We see this n to the 5th. That's only going to affect the endpoints, if there are any. The 3 to the n in the numerator is going to make the finite radius of convergence a third, but then the n factorial in the denominator is going to blow up that 3 to the n. So once we see factorials, we stop thinking about a finite radius of convergence. Unchecked factorials makes me think we're going to have an infinite radius of convergence. That's the thinking that's going with this. So we look at this, and we're thinking unchecked factorial in the denominator of the coefficients. That should make us think infinite radius of convergence. So this is just the thought process based on what we see. -2, this factor, this x plus 2 to the n tells us the center is at -2. A 3 to the n in the numerator means our radius of convergence is going to be 1/3 because we're going to divide by, we're going to have 3 absolute value of x plus 2 as the limit from the ratio test. But then this factorial in the denominator says there's a factorial, the factorial in the denominator without a factorial in the numerator to kind of cancel each other out means that we should have an infinite radius of convergence. So we're just trying to read the things that are happening. So we see this x plus 2, so we're thinking this factor tells us center, because that's what will zero out all the terms of the power series. If we plug x equals -2 in, that makes this 0 to the n, and so this is all 0. A 3 to the n in the numerator suggests a radius of convergence of 1/3. And n to the 5th in the numerator suggests that if we have endpoints, the power series will diverge at both endpoints. N to the 5th in the numerator suggests the power series will diverge at both endpoints. But then we get to the unchecked factorial in the denominator. So we're going to have an infinite radius of convergence. And so we just forget all this stuff. We don't care about the endpoints because there aren't any with an infinite radius of convergence. The 3 to the n is going to pale in comparison to a billion copies of 3 is going to pale in comparison to a billion factorial, because most of those factors are bigger than 3. And then the n to the 5th in a power series, the polynomial stuff only affects the endpoints. Just want to take each type of factor that we see and determine what it suggests about the interval of convergence. So let's suppose we have a power series that has 5 to the n. Let's have an x minus 3 to the n, and let's say square root, I'll have to go with, let's say n plus 1, so I don't blow up my power series in the first term. So just reading the factors that we see, x minus 3 to the n, this suggests that the center is at 3. The 5 to the n in the denominator suggests a radius of convergence is 5. And the square root of n plus 1 suggests the power series will converge at one endpoint conditionally and diverge at the other endpoint. There are no factorials, so this is the information that we'll go with. In the previous problem, I forgot to write down the interval of convergence is all real numbers. And that caused me to smear my diverges at the other endpoint.
Professor, I have a question.
Yes.
Why do we assume that it converges at one endpoint and diverges at the other? Is it because it's under the square root?
Yeah, it's a 1 over n to the 1/2 power. And so as a p series, square root 1/2 power diverges unless it's alternating. And that means the alternating endpoint, it will get convergence.
Got it. Okay, thank you.
So the center is at, it looks like there's a center at 3. It looks like we have a radius of 5. So I'll go 5 up and 5 down. So that makes the endpoints 8 and -2. So it looks like we're going to have between -2 and 8, we'll get convergence because the common ratio x minus 3 to the n over 5 to the n will be less than 1. Then we check the endpoints at -2. That's where we're going to have -2 minus 3 is a -5 to the n over 5 to the n. So -2 is the alternating endpoint. And 8 is the non-alternating side. So it looks like we're going to have -2 included with the interval of convergence, but 8 not included with the interval of convergence. So I'll say it's from -2 less than or equal to x strictly less than 8. We'll use a compound inequality because since the equalities are different, one is or equal to and the other is not, we don't get to use an absolute value inequality. This is what we would get if we were to run things through the ratio test, but we want to avoid writing down all those ratio test steps if we can just think our way through. Now, remember, this took a long time for me to talk about and write, but you're not going to be writing all this stuff down. You're just going to be looking at things and doing the problem at the speed of thought, which is very fast. Any questions? As you go through and pile more math onto the stuff that you know, one of the reasons that it becomes more difficult is that you have to remember everything that's gone before, and you have to kind of remember it in perfect detail. Or you have to remember what things are called so that you can look them up. That's the other important skill. Unfortunately for our heroes, for the most of the time, when it comes to testing your knowledge about math, we frame it in we go from the perspective that you have to remember everything that you've seen in perfect detail, all of it in perfect detail. And we don't emphasize calling things by their standard names so that if you forget something, you can look it up. And then we try to get around that by allowing you to bring a page of notes to the test. But the problem is the page of notes is custom designed for the test. So I've always wondered, I should be allowed to give you a page of notes during the test, but I should be allowed to put all kinds of extra stuff on it, and I should be allowed to put incorrect information on it, because part of knowing what the double angle identities are is knowing what the double angle identities aren't. And so that should be fair game. I should be able to write an incorrect quadratic formula, not because I want you to memorize it, but because I want you to look at one and know that it's wrong. It's less important to remember the details and more important to be able to decide which one is the right one and which one is the wrong one. Does that make sense? That would be, I think, a little too much work, which is why I really like the way that quizzes are structured in Canvas, because I'm like, well, hey, why don't I just give them a bunch of chances to do it? Then I'll just grade it and say, hey, do this over again. Because that's more like how we learn things. That's how we are supposed to learn things. If you're learning to play a song on guitar, you don't practice the heck out of the song and then say, okay, today is the day I test myself on this song, play the song, mess it up, and say, well, I guess I got an F in that song. That's not how it works at all. You say, oh, I'm still making a mistake, so I will go back and practice some more. So that would be the instructor saying, that wasn't quite right. On this particular section, use this fingering, or hold this note longer, or it's not an E flat. You know what I mean? And I don't see why school can't be that way, or shouldn't be that way. Actually, I know exactly the reason. It's because we don't pay teachers enough to make that kind of effort. And for a long time, we didn't really have the technology to implement that kind of a system where you just kind of keep training over and over again. And part of that reason is that our ratio is completely whacked. They'll put one expert in a room with 40 people trying to learn the thing. And then we have the chutzpah to say things like, we have a teacher shortage. And we just immediately start ignoring the core principles of how America works. If you want people to do something, pay them to do it. If you can't get people to do a job, maybe you need to offer more money to do that job. If you can't find people to work at your restaurant because we as a society have decided to pay them more money to stay at home, you need to raise your wages, not complain about society paying people to stay at home. If you want people to do something, pay them to do it. Simple. Incredibly cynical. I don't know if you've seen the movie Killing Them Softly, and it's incredibly cynical, but the thesis at the very end is kind of spot on, and we don't want to admit it. And it's especially distasteful because we put it in the mouth of a criminal. But we really don't want to see the truth in that. America's not a country, it's a business. Now pay me. If you want people to do stuff, you pay them to do it. If you actually value things and you want people to participate in those things, pay them to do it. If you don't want people to do things, if you don't want to pay people to do things, then don't turn around and start using capitalism as an argument for doing anything else. Because you can't have it one way and then change your mind when it goes the other direction. Anyway, that's just my thoughts on the matter. Maybe I'm wrong, I don't know. I would like the chance to run my experiment where we think to ourselves, where we like to say to ourselves, we value education. And so I'm saying free education is not going far enough. You want people to do it? This is America. Pay them. Pay students to be students. If we think it's that important, do that. You know what I mean? All right. That's going to do it for today. Incidentally, the reason I started disabling comments on YouTube, I don't think anybody noticed it, is I forgot that if you have public comments on YouTube, I thought it would be easier for people to comment on things if they started to want to do that. But all of a sudden, you find out that someone is paying someone to write a program that will spam YouTube comment sections with porn links. So I just had to disable the comments. It's not like I'm going to monetize this channel anyway. You know what I mean? Oh my gosh, I just realized I'm being a sucker in my own system. I want me to put videos on YouTube for people to reference later, and I'm not paying myself to do it. Oh man, I'm part of the problem. I guess Jeff Bezos would be proud of me. Work for free. Anyway, what are we talking about? We want to be able to read a power series and just determine. Now, if I took an n factorial and dropped an n factorial in the numerator of this one, so if I make that one adjustment, so we start off n equals 0 to infinity. And I'm like, okay, there's going to be an x minus 3 to the n. And you're like, okay, right here, we're going to go from 2 to 4 because it's a center of 3 with a radius of 1. Nothing else to say, all right? And then when I put this square root of n plus 1, so I go, all right. That's going to put the 2 in there, but the 4 is still out. Because the 2 is going to be the alternating side. 2 minus 3 is going to be a negative 1 to the n. So you're thinking, all right, that polynomial radical stuff affects the endpoints. Then I'm like, oh, hey, 5 to the n. It's like, okay, the radius isn't 1 anymore. Instead of going from 2 to 4, we're going to drop that all the way down to a radius of 5, so negative 2 up to 8. Negative 2 is still in because the square root of n plus 1 in the denominator. On the alternating side will be in for conditional convergence. On the other side, the non-alternating side, going to be divergent because of the p series. And then I go, okay, and also in the numerator is n factorial. And at that point, you're like, oh, dude, why did you not lead with that? Because an n factorial in the numerator is going to mean this converges only when x is equal to 3. Because if we run this through the ratio test, we're going to have the limit as n goes to infinity of n plus 1, and that will go to infinity regardless of the value of x. So the only way to get this power series to converge is to zero out all the terms. We want to be able to think our way through these problems so that we don't have to run a ratio test every single time. We're not robots. We're human beings. And when we see something and think our way through it, our mind, once we start getting used to it, our mind is going to go too fast. If we start trying to write things down, it's really hard to stop our mind from racing forward to the answer. And you see me do this all the time. I'm thinking about what I'm going to be writing next. I'm trying to talk, so I'm distracted. So I write just the next step and I combine the two together. And that's how mistakes happen. Anyway, that's going to do it for today. Check out section 9.5. There should be in your book a section 9.5. In problems 1 through 1,000, find the radius of convergence. And these are the things that you're going to look for. Your radical and polynomial stuff, your exponential stuff, and your factorial stuff, and your center. That'll do it for today. I will see you all on tomorrow. Thanks for playing.